It's always very interesting when someone stands at the mic, people go quiet, which is great. So we'll get started, if you don't mind, guys. Just a small bit of housekeeping. Maybe I'll move this down a small bit. So I'd like to welcome you to day 4 of Research Week 2025. Thank you all for coming along on this lovely Thursday afternoon. Just a small bit of housekeeping, if you don't mind. If you could put your phones on silent or airplane mode, if possible, just to give the speakers a chance. Thank you. You will see signs around the place. There's videography and photography happening. If any of you do not want to partake in that, you can contact any of us guys in the black and pink t-shirts at the back of the room. And yeah, that's kind of the housekeeping out of the way. So I will just like to introduce you to the event. Thank you, Hugh, Tig, and you guys for putting this together. It's really great to have this event as part of Research Week. Batteries and energy materials for a greener future. I hope you all enjoyed the event, and I'll hand over to Hugh.
Super. Thanks, Yvonne. And you already lowered the mic perfectly for me, so I appreciate it. That's all background, as Yvonne said. So just in terms of the layout of the day, or what we're going to do, I'm going to talk for about half an hour. People are okay with that? 30 or 40 minutes just to run through kind of the background motivation for what we're trying to achieve within this research centre, but also to give you a flavour for some of the different research topics that we're covering. So we'll talk through some nice large-scale projects that we have and some kind of high-impact publications across the different areas that we're focused on. So, after I do this presentation, what we'll do then is we'll take a couple of questions from the audience, if there are any, and then we'll do a panel session where you'll get to meet some of the PIs across the different topics within the AMPEiRE Centre. So it'll be a nice opportunity to hear from kind of the different interdisciplinary PIs that we have in the centre. So just by way of motivation, to give you kind of the global landscape here in terms of energy transition and what we're trying to feed into, I think people are very comfortable with the idea of this fossil fuel-based landscape that we have. So you see there down in the bottom left, that is our greenhouse emissions based on different sectors. Okay, so we won't go into the nitty-gritty of that. Maybe Darren will touch on it from a maths perspective later on. But what I'm trying to flag there is across these different sectors, the CO2 emissions that we have, it's very broad. So you have lots from, say, the energy and industry side of things. You have transport as a main producer of CO2, and we also have agriculture as well. So the idea here is that this CO2 production and these greenhouse gas emissions, they're a really broad problem that we need to address via multiple solutions. In terms of the transition, so again, here, kind of broad idea, I think people know kind of intuitively what the idea is here. So it's to move towards green energy generation and also storage across those different aspects that we have. So if you look at that graph down in the bottom right there, that gives kind of the predictions on some of the warming scenarios that we're looking at moving into the future up to about 2100. So what you'll see is this black curve that we started with down here. Again, this is kind of our historic scenario, and you'll see through all of these different scenarios essentially as they play out here. So you'll see this one here, and the orange target is the one that I just want to highlight. That is where we're looking at an optimistic scenario. So that is where we dramatically decrease these CO2 emissions over time. But the idea here is this can get worse. So we need to be aggressive in terms of trying to reduce these greenhouse gas emissions over time. So what can be done on this? I think most of you have probably come across the UN Sustainable Development Goals before, but this is a little bit of a reframing of this. So this is looking at climate action as kind of the central cog of all that, with the other Sustainable Development Goals built around it. So what you can see from this is it's integral to all of these different topics. So even on some of the broader aspects, things like no poverty, zero hunger, and so on, they're directly linked to climate aspects. So what we need to do is to facilitate all of these sustainable development goals. The climate side of this is super important. And again, in terms of the bullet points there, to emphasise that we need to have these solutions across a variety of different sectors, but also these need to encourage and facilitate changes at an individual level, at a societal level, and a global level as well. Okay, it's not just okay, for us to fix transport, we have to fix all of these different aspects because they're interlinked. So in terms of the motivation for us, again, it's this interdisciplinary angle that's going to facilitate the maximum amount of change. This can't be fixed just through science and technology. It has to have a broader remit and a broader contribution from different sectors as well. So these are probably my two favourite diagrams in all of my research. The first one is the periodic table on the left-hand side. I know some people here at least will be familiar with it. That essentially, as material science and as chemists, that's kind of our playground. So they're the elements that we have to play with in terms of trying to make sustainable materials, which is one of the main focus within our research centre. The one that you probably haven't seen is the one that's on the opposite side there. So what that is looking at is the elemental abundance that we have for these different elements. Okay, so this is arranged on a logarithmic scale. So the idea there is as you go up on that Y scale there is a lot more of that element as you go up the scale. Okay, so we'll hear the one element that's flagged there on the screen is lithium. It's shown down here. It's kind of around the middle of that graph. What you can see is any of the elements that are above that, there's significantly more of that element present in the Earth's crust. So we're looking at things, for example, along the lines of sodium, silicon, sulfur, which are much more abundant elements, and you'll see how this is woven in through the research that we do here. So within the sustainability angle, we have to keep that in mind, because to address these kind of technological challenges, we need to use materials that are more sustainable compared to what's been used at the minute. So what that kind of brings us on to then is this more future energy vision that you'll see. So what we essentially are looking for is we want to have this sustainable and local energy generation, but we also need to have a significant integration of energy storage and harvesting as well. So you'll see that nice cartoon that's shown there. The key part in all of this is really energy storage. So as you move towards sustainable energy production, things like wind energy, solar energy, you need to be able to store that for downtimes. So again, if there's no wind on a day, you need to be able to store your energy for another scenario. So again, a more integrated energy landscape like you see in that scenario, specifically on the batteries. So we always come back to batteries because they're a really integral part for this, but to have kind of a balance between what essentially is the performance requirements for a technology, but also the sustainability aspects as well. So if you look at the current lithium-ion batteries that are used in practically all of the devices that we know batteries are in, things like mobile phones, laptops, EVs, they're all very similar. Okay, so in terms of the battery chemistry that's in there, they're all quite similar. What's going to happen, what needs to happen, is to have a more tailored landscape where you have battery chemistries that are based on sustainability and match towards the applications that they're targeted for. Okay, so you'll see that diagram, might be a little bit small. It's kind of segregated into two different streams there on the right-hand side. So moving up to the top, you'll see that that's towards the kind of high performance side of the scale. So that's looking at EVs. That's likely going to be dominated by lithium-ion type chemistries as we move forward, because it's very difficult to beat lithium in terms of things like energy density and flat-out performance. But the bottom one, so this is another strand that you will see within AMPEiRE. This is looking at more sustainable battery chemistries. So what has happened here is there's been kind of segments within that technology tree where now within these battery technologies where you're looking at large-scale storage, you would look at more sustainable elements in there. Okay, so there's an enormous amount of material science and chemistry development that needs to be done to facilitate that change in the landscape. Okay, so give you a brief crash course on batteries, why this is all important. This is, again, a real motivating slide for us as chemists and material science of knowing what is actually going on inside batteries. Okay, we have gotten so used to batteries being part of every single day that we live that we aren't aware of the chemistry that's going on inside them. So even in a commercial lithium-ion battery that's in your phone, there are lots of complex chemistry problems and material science things that are going on over time. So the fact that your battery performance degrades over time, for example, that in 5 years your battery performance degrades by X percentage, is all related to real fundamental chemistry and material science issues in here. Okay, so we won't run through all of these things, not to terrify people, but there are lots of really interesting things that we can look at from a material science point of view to try and understand how to get around these failure mechanisms. Okay, so by understanding the chemistry that we have, we can build better energy storage devices, and that's one of the main things that drives us. So the take-home messages from this kind of intro part of it is on the battery side of things, it really is all about the chemistry and material science that we're looking at. There is no one-size-fits-all chemistry that we have, and that the battery chemistries and more broadly the energy storage devices that are being used, they should be tuned towards the application that they're being targeted for. Okay, so straight on then to the AMPEiRE structure. So this is the AMPEiRE Research Centre. So it's an internal research centre here in UL. So it's a multidisciplinary centre, okay, which builds on a lot of existing expertise here in UL. So it's based on many years of existing research, but it was only formally brought together last year. So we have a couple of goals here where we're looking to establish a really recognised global hub for excellence in battery and energy materials. We want to do cutting edge research, which we certainly do, and have an element of innovation within that that's facilitated by that interdisciplinary approach. So particularly during the panel session, you'll get to hear from people from completely different disciplines who are all contributing to that idea that we have. Within that, you'll see we want to engage them with industry partners, government agencies and international collaborators. So within all of the PIs that you'll see in the next slide, we have a really strong network across Europe and broader afield as well. Okay, so what we're trying to do then is address the specific energy challenges that are facing Ireland. So we have three co-directors of the centre, so Ty Kennedy, who you'll hear from later on during the panel session, myself and Professor Kevin Ryan. The current PI group, and I say current because this is expanding and we want it to expand, okay, that's just a cross-section of the PIs who are involved so far. So if I can do my maths right, Darren, will you double check? 21. 21, but again, we have a nice range of expertise that you'll hear from. We have people from a maths background, we have people from electrical engineering, we have people from more on the policy side of things. You'll hear from Connor later on, the circular economy like Yvonne, and we also have people from the economics and business side as well. So it's a much broader remit than we would have previously had in our little research silos previously. So in terms of the main themes, and we'll start to work through some examples of research from there, these are our 7 themes that you see here. So our top 3, there are kind of core expertise previously on the battery side of things. So looking at, say, advanced lithium-ion batteries, high energy density batteries, non-lithium, so that's more sustainable batteries. We have a broad theme around materials for energy-related devices. Then we have a nice kind of underpinning theme, which is around advanced characterization, monitoring and modelling. And then we have circular economy and policy and economic drivers. So you can see it's a much broader remit rather than just focusing on, say, specifically batteries. And we want to expand this as well and use the skill sets that we have within the PI group, but also the broader researcher group as well. And we've excellent infrastructure here in UL. Okay, so what I'm going to do, if people bear with me, is go through each one of these themes one by one and give you some nice examples for the research that's going on. It's not going to be all-encompassing because there is significant research in every one of these themes. So what I've done is just picked out nice examples of projects and publications as we go through to give people a flavour for what's going on here in UL. So in terms of the advanced lithium-ion batteries, so this is a real area of strength for us. So this is giving the SIGN Horizon Europe project as an example here. So this is a Horizon Europe project that's been coordinated in UL by Kevin. What you'd see in that map in the first place is this is a real pan-European project where we have partners across a number of different sectors and within different countries. So we have 16 partners. They're across universities, across research organisations, and small and large companies as well. So you see all of the logos around the map there. Really nice partners, including Ferrari. And that picture on the right-hand side is when we got to visit the Ferrari headquarters and do the tour of the Ferrari plant, which was pretty impressive. So the nice thing for us on this is, it might be a little bit small, that guy there, that anode component of the battery, so this is the negative electrode within our lithium-ion battery here, that is the UL contribution here. So what we have really good expertise in is developing these high-capacity anode materials. And through this project, what we're looking at is upscaling that material. So we have a lot of strong lab-based expertise, but bringing this up to the kilogram scale, as you would need for prototypes, is a serious challenge. So we have really nice partners who are developing, say, upscaling equipment for that and reactors. So we're now able to dramatically increase the amount of material that can be produced. We then have all of these different partners that are working on different components. So we have people working on the electrolyte, which is the in-between component here, and your separator, and you also have people working on the cathode. But what we also have within this is you have people looking at the recycling aspects of the project, you have people looking at prototyping, and we also have, as I mentioned, Ferrari and CRF, which is the research wing of Fiat. They're giving us feedback based on the end user requirements. So they want to move in and have moved into that EV space. So being able to tune the battery characteristics to match what they need is really, really important. Okay. We're doing lots of fundamental research within that area as well. So again, this is just, again, brief diagram here. What we're working at is these high capacity anode materials down here. What that allows you to do, let me step out, that is the existing state-of-the-art material in batteries is down here. Anything that's along this trend here has a higher capacity relative to that. So essentially we're making these higher capacity anode materials here in UL, and we're able to dramatically then increase the capacity of our anodes that we have. The paper that's down there, this is a paper that was published over a decade ago. Sorry, Tig, to age you dramatically, which was done during Tig's PhD. It was probably one of the first real star papers from UL on the battery side of things. And what was shown in this work was that when these materials alloy and de-alloy with lithium, that they form this nice porous network. So we were very much kind of looking at the material side of this. So understanding why we were able to get this fantastically stable performance. So what's shown here is over 1,000 battery cycles. So showing how this material was stable over that 1,000 cycles, and then been able to understand it from a fundamental materials side of things. Then just to show you some of the kind of high impact papers here. So this is work from Sumer, who finished a couple of years ago. So he did his PhD with Kevin as primary supervisor. So looking at silicon nanowires in this case, where you were able to grow them directly on these flexible substrates. And the idea here is that he was able to use these potentially for things like foldable batteries, wearable technologies, where you're able to harness that high capacity, but in a more flexible footprint than currently exists. Okay, so for theme 2, this is the high energy density side of things. So again, I have lots of plots and all this. This red zone down here, this is called a Ragone plot. The bottom of this is your what's called energy density. What essentially you want, where you want to be in this plot is you would like to be up here in the top right. So that means that you've high power and you've high energy, but things don't tend to work like that. So there will be trade-offs in terms of what's achievable with high power and high energy. But where we want to get is this red shape that you see here. That's where the lithium-ion kind of umbrella falls in. We want to be down here in this blue regime where we have higher energy density. So we have lots of activity going on here in UL where we're looking at things like lithium metal anodes and sulfur cathodes where we can increase this energy density. The thing to say, that second bullet point, so it says about mechanistic hurdles, there isn't really a free lunch when it comes to energy density. So as soon as you move to these higher energy density systems, there's going to be mechanistic challenges that you need to overcome. Okay, so that's where we come in terms of the science on this. Just to give you a feel for some of the numbers, so this is one of the newer EVs from Volkswagen. So the battery pack on that is about 86 kilowatt hours, range is over 500k. What you'll see from this is that your battery weight here is about 500 to 600 kilograms. Okay, so that's a significant mass in terms of the battery that you have here. The calculated energy density on that then is 164 watt hours per kg. So essentially what you can imagine is if you could double that energy density, which is easier said than done, you could dramatically increase the range of that vehicle from there. Okay? In terms of projects then, so there's a project been led by David McNulty, and it's an SFI pathway project where he's looking at lithium sulfur batteries, specifically using some of these materials on the silicon and germanium side of things, and from a mechanistic focused as well. Some examples here. So again, we're looking at these lithium metal anodes. So this is work from my own research group here. So what you'll see is, won't go too much into the depth, but these are a kind of a carbon paper that we have here. So what we're able to do is induce what's called lithophilicity, a nice word, one of my favorites, on this substrate where it usually really dislikes lithium. It will not go into that material. But if you coat it with these nanomaterials that I've been speaking about, hopefully you can see the video, what happens is that lithium metal that you see down here infuses into that structure kind of in a Terminator style infusion into the substrate. So what we're able to do is introduce this tuned lithophilicity into these substrates based on the materials that we coat on this. So we've done a couple of different studies including this, and what we're able to do in terms of the actual battery performance, what you'll see, this blue line that I'm drawing along here, that's our stable performance that we're able to get for a substrate that's based on this type of property, whereas these ones that you see down here, these are ones that don't have that mechanism included. Okay, so we're dramatically able to, from kind of the bottom up, tune that lithophilicity property and increase that performance. For these non-lithium kind of sustainable batteries, so I hope I've given kind of the background motivation for this. So as we upscale all of these different battery technologies, as more renewably produced energy comes online, we need to have an enormous amount of energy storage. So that's going to put pressure in terms of the availability of resources, things like lithium, transition metals that are used in the cathodes. So this really pushes towards the idea of things like sodium-ion batteries. So this is the Trident project that you see down here on the left-hand side. It's a nice collaborative project where there's development on the battery chemistry that would be one of the key expertise areas in UL, but also things like the battery management system and also kind of the integration of how this battery technology would really work in practice. Again, to give you a snapshot of some recent papers from this type of area as well, you'll see that there are a number of active areas. I've tried to give as broad a cross-section as I possibly can. So we have work that's ongoing in sodium-ion materials that you'll see up here. So there are two recent papers looking at different active materials for sodium-ion batteries. We also, another paper from AMPEiRE, who I mentioned earlier on, where he's looking at potassium-ion batteries. So as I said, all of these different battery technologies will have strengths and weaknesses. So what we've done in UL is built up this expertise across this range of different battery technologies over the years. Then in the bottom, so this is looking at kind of sustainably produced lignin-based carbon materials, and they're useful for things like supercapacitors, but also batteries as well. Okay, we're more than halfway through. Hope everyone is still with me in terms of attention. For this, materials for energy-related devices. So this is a broader theme, as I mentioned. So the idea here is looking at a range of these different, mostly bottom-up synthesized materials for specific energy applications. So you'll see this project that's highlighted in the middle. This is a Research Ireland funded project that Shalini Singh is leading. So this is looking at bottom-up synthesis of complex nanomaterials, again for a range of different materials, things like thermoelectric properties, catalytic applications as well. And it's using this really nice kind of synthetic approach where you're able to tune the composition to match the properties that you need. So it's this really fine control over the synthesis that allows you to tune the properties of your material. The one on the top left here, so this is a recent publication from Sarah Gearon's research group. So she is the recipient of an ERC starting grant. So what she is looking at is more sustainable materials for piezoelectric devices. So the idea here is that she uses a combination of DFT, which is a calculation-based method where you can essentially predict the properties of materials before you form them. So she has this approach where she will use this DFT method to essentially screen possible materials in advance, prepare them in the lab and test them and be able to essentially match her experimental findings back to those computational methods at the start. So it's a really nice approach where you can do screening in advance and then prepare your materials afterwards. Two other approaches down here. So this is more on the kind of complex nanostructure type materials. This was published recently from Shalini and Kevin. And then we also have in JMCA looking at tuning some of these dichalcogonide type materials, again from the bottom-up synthesis approach. Theme 5, so this is kind of a cross-sectional type theme that we have here. So this is looking at advanced characterization, monitoring and modelling. So you'll see down here, this is kind of what motivates all of this, in that this essentially is a cross-section of an actual battery that you would have in your phone, for example. So what you see here is this is all of the different layers and components that you have in a battery. That's your aluminium current collector, so that's the cathode portion. Then you have all of this kind of mass of the cathode component. So what you'll see here is you'll see the active particles, but you'll also see that you have a matrix that surrounds that. Okay, so it's a really complex layer that you have there with different particle sizes, with different additives and constituents within that as well. Then you have a separator, then you have your graphite, and that's the anode material that you see down here. So what we're able to do, and we perform mostly what's called post-mortem testing. So essentially you cycle your battery, you see when it fails, you disassemble it, and you're able to interrogate the things at a material level. So to bring you back to that schematic just before the start of the meat of the talk, I presented all of the different mechanisms that can possibly go wrong within a battery. So what we're able to do is diagnose those using some of the different characterization equipment that we have, particularly in the Bernal Institute. So you'll see up here, that's Sergey. He's one of the stalwarts of the Bernal Institute. So he runs here, that's called the FIB instrument. So essentially what it can do is create a cross-section through those batteries, and you're able to interrogate the materials from there. Down here at the bottom, so it's a little bit small, but what you can see is we do a lot of testing within these kind of coin cell levels. These are small little cells that would be familiar to most people. They look like a watch cell. But what we've been recently building towards is looking at these pouch cells. So within the European projects that we've done lots of upscaling towards pouch cells, and now through a couple of recent SFI infrastructure grants, we've been able to get the equipment that allows us to upscale these towards pouch cell level. So down here, what's important for us is you have all of these different length scales that are important for the battery. So you're looking from a cell level, which is, at the centimetre all the way up to the metre level, depending on the size of the cells, or the electrode rolls, for example, would very much be at the metre scale. Then you're talking about electrodes, which are at the millimetre to the centimetre. Your active materials can range from the nanometre to the micron, and then the atomic scale of what actually makes up the active materials that you have there. So there is this, again, I spoke a little bit about the periodic table being a playground for us. The idea here is that we want to interrogate all of these different battery technologies and also these energy storage technologies at these different length scales. And it's only through using these different approaches, the likes of the modelling approaches that you'll see here, our characterization approaches, that we're able to really move across those different length scales, with also contributions from things like mathematical modelling, DFT calculations. So there is plenty of room at the bottom here. In terms of two different examples within this theme, so we have some nice work here from Kieran McCarthy, who's a former PhD student here, and what he was doing is using EIS spectroscopy to look at things like the state of charge, the temperature, and the state of health for different battery technologies as well. With the characterization, so this is work from Kelly that was published recently. So what you'll see here, and the data isn't, in terms of the granularity of it, isn't so important. This is called operando XRD analysis. So the idea here is that you're able to perform XRD measurements, and try and move this in the right direction, that way. So as you cycle the battery, what you're able to do is take these XRD scans, and you're able to track what is actually occurring within the material as you're cycling it. So this for us is really exciting, because rather than having to create however many different steps are here, 20 different steps, and disassemble it and measure it at that stage, you can actually track it as the battery is cycling. So that's what we've really built up over the last number of years, is these operando testing and monitoring approaches. Theme 6, this is our circular economy approaches. Again, hopefully people are kind of familiar with the basic concept of the circular economy here. What we're trying to do is, this guy here is our waste stream, essentially minimize that. So you want to keep these materials at their highest operation level for as long as you possibly can. So you're taking your raw materials through effective design of the approaches, through things like reuse, second life, keeping those at the highest level of functionality for as long as you possibly can. There is a nice project here, again, funded by the SCAI, which Kevin is leading on battery recycling. So looking at, again, what the best case scenario or what the correct approach is here. So what you can, for a battery EV, what's typically judged to be the end of life is when your battery is at about 80% of its starting charge, okay, in terms of its range or its capacity. So what you can imagine from there is it's almost like a trickle-down effect. So essentially you still have a really well-functioning battery that has significant capacity that it can deliver. So you could maybe move it into something like these second life applications where they're slightly less demanding. But there's also scope then to recover the materials and recycle them. So there's things like direct recycling, for example, where you would immediately almost regenerate the material and put it straight back into new batteries. So working out the logistics of what the correct path through this life cycle is, it's a really important aspect. There's also a project here that's been led by Colin Fitzpatrick. So looking at this again as a slight departure from kind of the previous core expertise that would have been in the battery research. So looking at things like robotics and artificial intelligence to identify batteries within some of these smaller goods as well. So within that whole battery recycling, I will say, zoo or landscape that's out there, it is a really messy scenario because there's so many different battery chemistries that you would have in a sample of mixed batteries. They'll have different states of health, they'll have different materials that are available within them, so they're developing nice approaches here to try and segregate out those different waste streams. Last but not least is on the policy and economics side of things. So with all of that said around the technology side of development, it is really important around things like public policy, economic drivers and incentives for bringing those to society. Okay, it's absolutely no good if you make the best EV in the world if people don't want to drive them or if they're de-incentivized from driving them in the first place. So really trying to build in this kind of societal or community acceptance of energy infrastructure is really something that we're very interested in and a topic that I think is going to grow a lot within UL. And the final thing to flag here, there's a very nice output you'll hear from Conor in a second around the public policy side of things and how this BESS or battery energy storage systems, how they can be kind of incentivized for people and looking at Ireland as a nice case study here. Okay, so in terms of the summary for me, what I wanted to do at the start was just give you kind of a broad motivational summary from our side. So what the importance is for this global energy transition, the fact that it is built around these different technologies, but also it's underpinned by all of these societal, economic and policy factors as well. The greener technologies that we are contributing to here in UL, they need to be applied across a range of different areas. So that's in terms of things like electricity generation, transport, residential and agriculture. For the AMPEiRE Centre, it was great to introduce it to a broader audience. So we've met internally as the AMPEiRE Centre, but to do it more broadly, we have a real core skill set here around energy and battery related research, but expanding that out to new avenues, particularly within the funding landscape in Ireland, for example. So the rebranding of Science Foundation Ireland as Research Ireland, they have a real focus on interdisciplinary research. So we want to be attractive in terms of securing funding, but also doing really exciting research within that as well. And I've given you kind of hopefully a nice cross-section of some of the high-impact research that we have, the large collaborative projects, and some of the new ideas that we are coming up with to try and combat climate change. So, if people have questions, I'm more than happy to answer questions before we move over to the panel discussion.
BYD have made a lot of progress with sodium-ion type batteries. So, but how much would they have to reduce in terms of cost to be competitive from energy storage at the power plant level or from current pricing?
Yeah, that's a really hard question. And the thing is, it's such a dynamic field. So, and with people like BYD, you only find out about it once you read a newspaper and you see their latest claims. So it's absolutely fair to say that Europe is lagging behind compared to some of the different countries. In terms of exact numbers, I don't have a feel for it. Yeah. Any other questions? Hi, Noreen.
Have you done any studies on the reversibility of your electrode materials around? Have you done any CE work?
We have, yeah. So a lot of that would be on kind of the fundamental mechanism. So you can track the potentials at which the different reactions go through. So for absolutely, you saw TIG's data there. It's more than 1,000 cycles reversibility. And if you were to look at either the differential capacity plots or the cyclic voltammetry, you would see that they're reversible. They occur at the same voltages over time, the same processes. Yeah. Thanks. Okay, so I will use that as my lead in. So hopefully the more exciting part will be now get to meet some of these researchers and to hear from them. So Tig is going to chair this session where you'll hear from Darren, who's an associate professor in the Department of Maths and Stats, Ibrahim, who is in the Department of Chemical Sciences. Is Ibrahim here? He's there. Conor Little, who's an associate professor in the Department of Politics and Public Admin, and Yvonne Ryan, who's an associate professor in the Department of Chemical Sciences. Okay.
Okay, so thanks, Hugh. Very, very nice overview of AMPEiRE. Just to kick us off, I'd like to introduce our panel in a bit more detail. So starting at the end, Associate Professor Conor Little. So Conor is an Associate Professor in the Department of Politics and Public Administration. He was awarded a PhD by the European University Institute in 2014, and before coming to Limerick worked at University College Dublin, Keele University and the University of Copenhagen. His research interests include the comparative politics of climate change, political parties, political careers and Irish politics, and he regularly supervises research projects in these areas. He initiated the Irish Policy Agendas Project as part of the Comparative Agendas Project, within which research aims to measure the allocation of attention to policy issues across multiple institutional, political and societal agendas, and to use those data to understand policy and politics. It measures the allocation of attention to policy issues on the island of Ireland. They analyse those data and they provide code books and data to support public policy research and education. Next in line is Associate Professor Yvonne Ryan Fogarty. So Yvonne is a Research Ireland Pathways Fellow and an Associate Professor in the environmental science within the Department of Chemical Sciences. Her research expertise is industrial ecology and material flow analysis, focusing on challenges facing the emergent circular economy. Her work addresses high environmental impact waste streams, hazardous components, and product demand for critical materials. She was nominated by the Irish Government to the Open-Ended Scientific Group on Effectiveness Evaluation of the Minamata Convention on Mercury, as she contributed to refining the Mercury Inventory Toolkit in products to waste material flows. And as part of the E2E project, she worked with policymakers and the scrap metal industry to develop a material flow analysis protocol that was inexpensive and non-disruptive to waste management business operations. This methodology is currently used and cited by the Irish Environmental Protection Agency to report waste statistics to the EU. Next in line is Dr. Ibrahim Sana Aminu. So Ibrahim is a material scientist and also a Research Ireland Pathways Fellow and Principal Investigator in the Bernal Institute in UL. And his research focuses on the synthesis and development of advanced nanomaterials for next generation metal-ion battery energy storage systems. Ibrahim earned his BSc in Materials Engineering from KNUST in Ghana in 2008 and a PhD in Material Science and Engineering from Wuhan Institute, University of Technology in China in 2017. In 2018, he joined the Bernal Institute with a prestigious Marie Curie Individual Fellowship, having obtained almost 200,000 in EU research funding to investigate porous graphitic cathodes for aluminium-ion batteries. Since then, he's been a serial successful awardee of research funding. He was awarded an SFI Industry Research and Innovation Fund to lead a project on failure analysis of magnetic sensors at analog devices. And in 2023, he secured the SFI IRC Pathway project to develop functionalized carbon nanofibers for aluminium-ion batteries. And last but not least, Associate Professor Doireann O'Kiely. So Doireann is an applied mathematician with a particular interest in fluid mechanics and elasticity. She's an Associate Professor in Applied Mathematics at UL and co-director of MAXI. Her work focuses on the mathematical modelling of real-world systems with special emphasis on fluid and solid mechanics and chemical processes. Her methodology involves using differential equations to describe the physical rules governing a physical system, and then using a range of mathematical techniques to analyse those equations, giving both quantitative predictions and qualitative insights. This approach lends itself to a number of real-world applications, including manufacturing pharmaceuticals and energy storage systems. Her main work to date in the energy space has focused on predicting the expansion and contraction of electrodes in lithium-ion batteries, specifically in alloying materials, which in UL, in our research groups, we're very familiar with. But she's interested also in the exploring of a host of fundamental science questions triggered by modern energy challenges and innovations. So you're all very welcome, very well-credentialed panel, I think you'll all agree. So to start off, I'd just like to ask a very general question to everybody. So Hugh has done a great job outlining the research focus of AMPEiRE. But I'd like your opinion, and maybe starting with Conor. Why does the research within AMPEiRE, why does it matter? Why should the public care? And why should the university be focusing on this type of research, in your opinion?
Can you hear me? Yeah. Okay. I suppose it addresses a set of very big problems, right? It aims to provide knowledge that's going to help to address those problems. So we have the climate problem, which you referred to. We have keeping the lights on, right? We have just energy problems, so stabilization of the grid or other aspects of the energy problem. And then we have the materials sustainability problems, right, which are very, very real, very human impacts, right? And so being able to shift from, to, for example, sodium ion, it can have enormous economic and social effects. And so those are the kinds of reasons why the public might care about the kind of research that we do. Yeah.
Thanks, Conor. And Yvonne?
Yeah, I think we're at we're at a real different phase now with battery technology. So many members of the public are actually owners of large batteries. So it's parked outside their front garden. It's charging, and they know what they think they know what they do. We talk about recycling and recovery, but what we're really talking about is collection. And there's so many, we're at the crossroads now where you've got EU legislation like the Eco Design for Sustainable Products and the Batteries Directive, all feeding into trying to bring batteries really into the circular economy. And this is going to be a fundamental shift in thinking for everybody and practices. So we've evolved a system that is a waste management system essentially, and now we have to start really rethinking about how do we view products at the end of life as a resource and retaining that valuation throughout the product's life cycle until we get the absolute maximum out of materials. But before all that happens, we have to actually consider where the materials come from, where they are going across the entire lifespan. So really for the public, they're at that interface of using the product, and where they can be given options to repurpose it, to use it to its maximum potential. But then policymakers have to be there to bring in the supporting policies that allow that to happen, right? And the same, this is where research, I kind of made this little note to myself. That's why AMPEiRE is so important. It's the fundamental chemistry that determines where the materials come from in the first place. And it's the chemistry at the end that determines what you can do with them at absolute end of life. And that's why this research is so important and matters so much to everybody.
Very good.
Sorry. So I think the two speakers, including you, almost covered everything. But what is important is to ask who owns the center. Is it the researchers in there or the public? So it's funded by public money, so they have every right to know what is going on in there. Besides the technicalities, we know in Europe, for example, the contribution of Europe's share in battery manufacturing is nearly negligible. So this is important for the public to know there's hope in the future. So just to keep it short. Yeah.
Thanks, Ibrahim. And Darren?
Look, I mean, I guess it's all been said, but the ultimate thing is we know that the way we're operating as a society right now is doing harm. It's doing harm to nature. It's doing harm to our children and grandchildren. It's doing harm at an obvious physical level and at an implications level in terms of political and economic stability. And there's a lot of things we need to change to fix that, but energy storage and batteries is a big part of it. And there's the kind of things that we're conscious of because it's in our pocket, like the energy storage and the life cycles, and then there's the things that most of us don't think about, like the start and end of life, and it all matters. And one of the good things about AMPEiRE is that it's looking at that full picture.
Great. So a more focused question, I suppose, and I'll start with an area I'm very comfortable, so stick to what you know is always good advice, I think. So, Ibrahim, I'll ask you first of all. So, the research in AMPEiRE, fundamentally we want to be developing the next generation of battery technologies, okay, while doing that in a sustainable manner. I'd like to get your opinion. There's a variety of chemistries being developed in UL and globally, in research groups around the world. What to you, in your view, are the most promising materials directions for Ireland? And where do you see will be in terms of the battery landscape in 10 years' time and beyond?
Wow, that's a loaded question. Yeah, so for the next decade. Okay, so just to put it in context, right? So the energy consumption of Ireland is, from the Energy Sustainable Authority of Ireland, is about 167 to 170 terawatt hour. So of this, 43% comes from, it goes into transport, electricity about 23%, which is roughly 37 terawatt hour. How about the share of renewable energy? So the share of renewable energy in this is about 14%, which is around 23 terawatts. So based on the European Union's requirement on renewable energy, Ireland is supposed to achieve 43% by 2030. That is just 5 years away, and we are at 15%. So it means something must be done, and fast. So at the moment, if you consider the EU Green Deal, it says climate neutrality by 2050. But the chart here shows that by 2050, even globally, we are not going to get to that point. So that means every country must be up and doing. So if you look at the COP24, the Climate Action Plan for Ireland that was released in 2024, the aim is to reduce greenhouse gas emissions by 51% by 2030, which are high targets. I don't know who made those targets, but they are not achievable, in my opinion. So the question then is, if Ireland is going to contribute to the green economy, the green policy that is laid out by the EU, what can be done? Right now, considering the fact that the EU does not have limited access to key elements in batteries, like lithium and cobalt, in my opinion, the next area that we should be focusing on is what can give us energy security and sustainability, and that will be non-lithium based batteries. That is not to say we shouldn't be looking at lithium batteries, but the focus there would be shifting towards reducing what is needed to increase the limit for the EU or Ireland. So I think for in terms of materials, should be materials that will lead us to high energy security and sustainability in non-lithium chemistries. We can explore new areas like multivalent element-based battery chemistries. I don't have any specific material to give because I think carbon will be one of the easiest ways to mention, but we know carbon oftentimes will not give us the energy density that we want. But certainly it's a good point to start with. Yeah.
Okay, great. And so for those future technologies, materials discovery is going to be a huge component of that. So we're going to need new materials. So a question for Darren then is, how can mathematical modeling accelerate that discovery? Because there is a lot of work in that area currently as well.
Yeah, so I guess accelerate is the key word, right? Yvonne made the point that it all comes back to the chemistry from the start to the end, and modeling, in terms of mathematics and statistics, its role is to help the chemistry get there faster. And I think that comes in a number of places. One is at the very start, there's a huge startup cost to exploring a new technology or trying to design a new, whether it's a new geometry, a new chemistry, a new way of laying things out, a new way of putting things together. That takes time, it takes money, it takes PhD students, it takes resources, and sometimes it won't work out. And one thing that a model can do is help you at a very approximate level say, I think this is roughly what's likely to happen, and that's a go or it's not. And so you can screen out some things that are going to be a waste of time before they even start, or you can explore some potential ways of doing things that are far beyond current technology and say, yes, that's going to be a huge investment, but it's worth driving towards. And then the second place, and this is something that I would see as kind of statistics, so James Sweeney sitting over there, and this will be more his strength. Once you're at the stage of trying to develop and optimize things, and you're saying, okay, if I tweak this, what happens? If I tweak this, what happens? You're still spending huge time and energy costs if you need to try out 100 or 1,000 different scenarios. And so what you can do is you try 10 things and you say, okay, based on these 10 observations, where should I be looking? Where should I be doing my tests? What parameters should I be focusing on more and more and more? And what parameters are not worth my time in terms of further investigation? And so I think those are areas in which modelling, it's not the star of the show, it's a supporting role, but I think it's a really important supporting role.
Okay, great. And with these new technologies, like clearly we will be moving beyond lithium ion, so lithium ion is here to stay, and advanced lithium ion, but there will be other chemistries coming down the line as Ibrahim has laid out. So Yvonne, this is for you. So currently we're not doing a great job of recovery and of recycling of lithium ion, let alone lithium sulfur or lithium metal batteries or sodium ion or potassium ion or whatever is coming down the line. So how well do you think Ireland are prepared to implement recovery, reuse, recycling strategies for current lithium ion technologies and future technologies?
Okay, for current lithium-ion technologies, I guess it's all about like a chain of command and a chain of ownership. So, you know, some of the examples that were illustrated there, especially with large industrial batteries, we know where they are. We can approximate how many of them there are. Same with EVs. You know, every EV is registered. We can track that. We can measure that. We know when they're coming to the end of life. We can model and predict for that, right? It gets tricky when you get down to the smaller batteries, of which there are so many, and they all have a huge potential. So we've seen this with, it's a similar scenario with e-waste. So we've developed like really good characterization and collection techniques for e-waste. And one of the, you know, there's the biggest problem at the moment with e-waste is like the big things like your fridge, your washing machine. You can't hoard one of those, right? You buy a new one, the AMPEiRE scheme takes it back, it goes to the recycling centre. It goes into that chain of command and control, and it's dealt with, right? But smaller things, and where the producer responsibility organisations now are really running into difficulty, is small e-waste items. And there's many of those. So you may have one car, right? But if you think about all the other battery devices that you have in your house, in your ownership, in your possession, that you cycle through much quicker. Lots of these end up in household waste collections. Now we're kind of like, I want to speak about one particular project in particular, and that's the iCycle project. So it's the e-bikes project that we have on campus. And that's looking at kind of a middle-sized battery, right? It's bigger than your household stuff. You can't fit an e-bike in a bin. But they do kind of go missing, right? They end up in places that we don't want them to. They end up in scrap metal. They end up in skips. They end up frequently in the bottom of canals. Stuff like that's wasted potential. That is good battery technology that's gone somewhere bad. And that's kind of what we need to be looking at as well, is every one of those cells that has been charged up, at the moment, the way our grid is, it's been charged on fossil fuels. That has an environmental impact. That cell that was, you know, manufactured and made from virgin raw materials that were mined somewhere, that has an environmental impact. And we talk a lot about carbon, but we also need to consider toxicity. And that's where we have to get into these really much cleaner battery technologies and much cleaner, you know, initial starting points for fabrication. And again, that they are designed much better. The shame really is that when a battery enters use, is that it's so important that its use is extended over time. So this is the circular economy kind of principles. We want to narrow flows. We want to use the least amount of materials as possible to deliver the best possible benefit. We want to extend product lifetimes so that your battery lasts much longer. And then at the end of that life, that it can be assessed and put into a new application. So, and then choosing the suitable applications for some people, it's trying to employ all those ors. Can those batteries be remanufactured? Can they be repurposed? Can they be reused? Can they be readapted into something else? So, perfect example of that is the EV battery that becomes storage in the home. We need to start thinking about other applications. The batteries regulations at the moment, it's interesting because we are now finding newer and newer ways to use batteries and products that weren't thought of before. So, for example, like the e-bikes that are a light means of transport, the Batteries Directive is now trying to figure out a way by which we can assess that market, assess the use times, the product lifetime we actually don't really know the product lifetime of an e-bike, which is a massive problem, because if you don't know when peak end of life is going to be, you can't plan for effective collection and recycling and reuse. So there's so many elements to this. There's so many data gaps that this research is just so essential. It's essential to start joining and connecting all these dots and start really thinking about imaginative possibilities that we can deploy, and deploy rapidly. We are running out of time.
You mentioned regulation there. So for Ireland, like, how much of a leader can we be on this, Yvonne? Do we have to wait for the EU, for a directive from the EU, or can we plough ahead? Or
I don't think so. I think we have to actually recognise that we have a very unique set of circumstances here. So that's one of the things that actually came out of our research on the e-bikes, is that we lagged behind in uptake of e-bikes. That's also led to a better situation, because we actually got some better, in terms of the waste stream, we probably got some, the less reliable products would have been cycled through on the continent first, and we got the better bikes by virtue of the fact that they've survived the product initiation stages. It also presents a challenge, it presents a unique opportunity for us to really engage localised methods of keeping products in circulation longer. You know, local supports, local repair shops, local ways of promoting, you know, state of battery health. That is impacted by user behaviour. It's impacted by leaving your batteries out in the cold. Can we better inform people on how they manage their batteries? How can circumstances and consumer behaviour serve to elongate those lifetimes? And I think that actually with the batteries directive, it seems to me that if we can come up with innovative solutions, it looks like the Commission would actually listen to that and take that on board. For example, the collection targets are now changing from collected to available for collected, to actually reflect the fact that we don't know the product lifetime. So we are trying to estimate that. And if we can estimate it and extend it, that's a good day's work.
Great. So I suppose you're talking about those medium-sized batteries. Conor, your research has looked at the large-scale batteries, so the BESS systems, so the battery energy storage system. So for the uninitiated, these are kind of truck container-size batteries that are used for stationary storage of renewable energy, and that's critical because you know renewable energy is intermittent by its very nature. So in times of you know, low wind, or you know, when there's not much sun out, you need to have a store of energy. So that's where these BESS systems can come into play. So you've looked at comparative analysis using Ireland as the base, and comparing, you know, policy in deployment of BESS systems across Europe. Can you tell us, you know, what has Ireland done well in this area, and maybe what can we learn from other countries?
Yeah, sure. So Ireland, you know, for its size, has quite a lot of stationary storage, right? So I mean, it's still in its infancy in most countries, right? But in that sense, and very provisionally, we're a leader, right? Although this changes every year, right? The deployment of grid-scale batteries is so fast, and the pace of that is accelerating so quickly that these figures change in very big ways every year. What I suppose the things that we've done well, I suppose there are two things I pick out. One is we don't have a full range of revenue options, right, for owners of grid-scale batteries, but we have had a scheme in place, the DS3 scheme, for the last number of years, right, and that has provided economic incentives for people to invest in this sector, right, and so that's been effective up to this point. And then the second thing is the wider context, right? So having an ambitious renewables policy and climate policy around this, right? So that provides confidence to investors in this sector, and also the renewables to a great extent drive along the grid scale batteries, right? So the grid scale batteries come with the renewables, so it's a byproduct of renewables policy and renewables deployment. So those are kind of two good characteristics of the Irish case. I think in terms of what we can learn from other places. So we produced a report last year, and a number of months after that, DEC, the department, produced a electricity storage framework policy, and they're drawing on a lot of these lessons from elsewhere. And so it's about providing new markets, right? Because these markets don't just develop organically; they require policy intervention, right? They require regulation and so on. So providing new revenue opportunities for owners of grid-scale batteries, so like spot markets, so intraday and day ahead. These are things that I don't know very much about, I must admit, but they are options that exist in other countries, and that provide incentives for investment in this sector. Another thing that we can learn from other countries is that some of the leaders on grid scale and on batteries generally also very strong research and development support, right? So in terms of spending on research and so on. So if you look at South Korea, if you look at the UK, and also an innovation ecosystem, right? So that's another kind of facilitating issue. And I'll just emphasize a third thing as well, which is that policy development is for the medium and long term, in the sense that the policies that we adopted in the early 2010s are shaping the deployment of grid-scale batteries now in Ireland. And the policies that we adopt now will shape the deployment of batteries in 2040. So we have to think ahead to the level of ambition that we have for a time like 2040, and I suppose shape our policies around that level of ambition. And it's a very high level of ambition that we have, as Ibrahim mentioned earlier on, right? So they're policies that will be with us for a while. Yeah.
Okay, so clearly it's like turning the Titanic, I suppose. These types of things are very, very slow to move. So as Ibrahim has laid out those really ambitious targets for 2030 and 2050 and beyond, do we need to be more aggressive then in our policy framework and how we develop it, do you think, in your opinion, or are we on the right track?
I don't know if aggression is the right term, but I don't know. I mean, there are earlier movers and there are later movers, right, on these things. And so if you look at California, for example, it's not only deployed a wide range of supportive policies in this area, but it also moved earlier than most other places. If you look at China, it's the same thing, right? So it is about, timing. Timing really matters, and that's a big part of what makes a leader. So maybe nimble rather than aggressive, but yeah, I think. I think that in this sector as well, it's not a very politicized sector, right? It's an area that we would call kind of an area of quiet politics, right? Where regulators, civil servants, get on with the business of doing this. Of course, there are interest groups involved as well, right? But it isn't a matter of, and a lot of them are working just to solve problems, right? So obviously firms and interest groups want to make a profit, but a lot of the regulators and civil servants are working to solve problems like a low level of interconnection and the kind of vulnerability that gives rise to. So they want a stable grid and they want to achieve the climate targets. So I don't think it's a matter of being more aggressive or trying to win some kind of a political fight, right? But on the politics of it, what we do need to look out for is that it can become a salient issue, right? Particularly for local projects and so on. And so there is a hearts and minds side to this. So you need to convince people that the waste is going to be looked after and that the batteries are safe, right, and that they'll be managed safely. Because there have been local cases in Ireland where projects have been turned down for planning because of local campaigns against them. And Philip Badger-Hayes from RTE has done some good journalism around that for a project in Kildare. But that's the kind of politics that we have to look after, is to create a realistic and positive impression of the role of batteries in solving these big problems that we have to address. Yeah.
Okay. Great. So to move back maybe to the technologies themselves and to reference back to things that move slowly. So often research at lab scale can move quite quickly, and then commercializing that, getting that into a finished product can be quite slow. Ibrahim, you're experienced in this. Can you talk a little bit about the challenges with scaling from lab breakthroughs into an industrial application or to commercialization? What are the challenges, and how can we kind of overcome those?
Wow. So the challenges, not just for batteries, but basically for almost anything that you want to move from lab to industry is quite challenging, but it's especially more challenging for batteries. The reason is quite simple. Because you have 4 major components of battery system, and each of these components have unique problems. Once you bring them all together, they form another new set of problems that you must solve. And trying to get all of that done in the lab before taking it out is quite challenging. But from the lab perspective, one needs to think of an integrated approach where you would combine scientific innovation or material discovery with industrial feasibility. So what that means is that materials that are being developed and processes must be manufacturable. And when you are able to manufacture this, that means if you are able to, like some of the projects that you displayed there, they were developed with industrial partners. So this is a key way of getting some of your work being validated by industry, because they kind of guide you as to what is needed. But all of that will not be enough to solve the problem, because at the end of the day, you want to have somebody who is willing to say, I like this, I'm going to accept it, and I'm going to support you to develop it into a real product. So without this, I don't think it's going anywhere.
And that can be the tricky part. So
Yeah.
how do you convince, let's say, an auto manufacturer or even just a battery manufacturer to adopt your technology?
Yeah, so to convince somebody, especially who doesn't have any prior knowledge of your project, they will need data. Data is the first point. And with battery, all the data you'll be providing would be lab-based. Then they will have to question what happens with scalability. And oftentimes you produce fantastic materials at the lab scale, it works perfectly. Once you begin to scale it, then you are introducing new challenges with respect to material properties, uniformity of your product, performance, and then it becomes a big challenge. They would also want to know, can you scale it, and at what cost? So all of these challenges that you must address before they even listen to you. But the important thing is going out to talk to the people, to know the problem before you think of calling yourself, putting yourself in the journey of scaling. Otherwise, it will be exercise in futility. Yeah.
Very good. Darren, to talk about these kind of future battery technologies. So you've done work on, mechanical challenges, I guess, for alloying materials. And alloying materials for lithium-ion batteries, for example, they can hold a lot of lithium, but there's massive volume expansion, so 300-400%, which can lead to limited cycling life. So you've done work on the modeling of those systems. So for future technologies, where do you think modeling can come in at the materials level that it will accelerate their adoption?
So it's a sandbox, I guess, and so the materials science, I can't change that. But what I can do is I can think about how should I structure it? What layout should I use? What happens with scalability? And not necessarily at the kind of commercial level, but literally what happens if I double the size? Should I expect everything to double, or is it more complicated than that? And that sounds a bit trivial because it's much less existential than a lot of the other questions, but it helps you accelerate, and it all comes back to accelerating for me. It helps you say, okay, the mechanics are a huge problem, how can I offset them? So I guess the research that you referred to, geometry was a huge driver in that, because the geometry was different to anything that people in my world had been thinking about before, and not just the geometry in terms of the shape, the geometry in terms of the order that the stuff was put together in. And that had huge implications for what effect the stresses had. So stresses we know are bad, but stresses also cause things to happen. They cause stuff to move around. And normally that's something that slows things down. And in this case, it was something that sped things up. And you would never, ever, ever, I think, have seen that stresses were the driver there without the modelling, because it allows you to look at things at a scale where you can't measure. You know, this idea that if you want to see the stresses inside of something, well, stresses aren't something that you see. You don't get to look at a piece of material and go, oh yeah, that looks like about this number of pascals, or not this number of newtons, this number of kilograms, this number of whatever bending moment I'm worried about. You don't get to do that. And especially inside of a battery, you don't get to do that, because every time you want to take a measurement, you have to stop whatever you're doing and cut it open. And then we've talked about this, you hope that that doesn't change what's happening inside the moment you cut it open, but you know it does, right? And then you try to take a measurement and you hope that taking the measurement doesn't change it too much, but you kind of know it is doing something.
Schrodinger's battery, I guess.
Yeah, exactly. Yeah, and so the maths, I think, lets you dig inside of things and look at what's happening at a small scale. What does that tell me about what will change when I make changes? And what does that tell me about where I should go? Ultimately, that's what it comes down to. And it can be in the mechanics, it can be in the chemistry, and you talked really nicely about this thing across different scales, and I work at this scale of mechanics and stresses, and Sarah Gearan, for example, works at a much smaller scale, but the advantages are the same, that you get to understand things that you can't actually see or measure easily in the lab.
Great. And to come back again to you, Yvonne, for the final question, I'll give you the honour. So I suppose for these future technologies, there's going to be new materials in there. You've already discussed the challenges with the circular economy aspects of those. As we move to new materials, those challenges are going to be exacerbated. So, can you talk maybe about systemic barriers that exist that are kind of causing additional challenges to recovery, reuse and recycling? And how your research maybe can help us overcome that.
Yeah, okay, so batteries are, when they come to end of life, they're typically classified as a hazardous hazardous waste material, and that's, I suppose, how I've gotten interested in this area. Before, again, like I mentioned, our challenge was, because batteries contained hazardous materials, our early battery technology was lead, mercury, those really, really nasty things that you do not want in your environment. And the idea was, capture this stuff and, to quote Father Ted, get it as far away from us as is possible. And that was the approach. And we just have to completely break that mental, thought process about waste. So that's luckily we have REACH, and we have the restriction of hazardous substances now. So that is driving the cleaner, greener chemistry. So there has been an impetus from from the other side, right, into the chemistry to get it cleaner and greener. And now what we have to do at the end of life is develop the chemistry to fundamentally disassemble things again and to regenerate all those materials again. That is a barrier, because, you know, like we know, commercially available products, like the example that was given of BYD, you know, you've got issues with we don't know what's in those materials really. We have to establish what the exact things are so that we can put in place a process that, you know, you're often then going back into looking at smelting of materials and again adding a huge amount of energy to regenerate things. So this sounds very unhopeful, doesn't it? But it's just such a massive challenge. It's something that is so cross-disciplinary. You can see that every discipline has to be involved in this. My other kind of big worry is rebound effects. And I, you know, for example, this is why universities do research, is because we are a place of education as well. So much of what we research bleeds into our teaching. And it is, you know, we get to inform the next generation of environmental protection awareness officers, of licensing and inspectors. We get to tell them about the upcoming challenges and inspire them to be cognizant of them and to policy make for them and to, you know, to be aware of what's coming down the line. Conor mentioned planning and environmental impact assessments. That's so important. The Critical Raw Materials Act is upon us. We can see huge turbulence in that area. We now have that responsibility that we always had. Now we have the impetus to really make sure that what we mine, what we extract, what we use is used properly, used responsibly, used extensively and used well. And at the end of its days is that we can actually, we are net zero impact as opposed to net zero carbon. We have to get to cross all those bases. You mentioned Sarah's research where she uses computer modelling to screen materials for batteries. Yeah, we need an environmental impact inside on that as well. And I know, like you've done some work and Tig with recycling of plastics within battery cells and things like that. That's where we need to be going, those really innovative ideas. And we need the space to explore that. We need the time, but we actually are running out of time, so we just need more space, more people, and more of a drive on it. And it's there, the knowledge is there, it's in this university. We see every year, we see more students engaged and interested. The kids are okay, is what I keep thinking. They're inspired, they're ready, they want to do this work. We just now need to give them the space to do it, and the guidance and the mentorship to bring it forward.
Excellent. Well, I think that's a great place to finish, a call to action for everybody, I suppose. You know, we need to get off our butts and, you know, make things happen here. We'll finish there. I'd like to, you know, really thank sincerely the panel for sharing their expertise with us today. I've learned a lot. They're clearly experts in their field, and I hope you found it very useful. I thought it was very insightful and informative. So thank you very much to the panel. Before we finish, I think we'll open up to the floor for questions if you have any. So, Bree?
So I think with Ireland we have like a huge amount of potential for renewable energy because we have like potential for solar, wind, hydroelectric, and therefore we should be emphasising on Irish businesses that, you know, focus on renewable energy, energy storage, energy monitoring, energy shipping. But I think, would you agree that this isn't just important for climate action, but because of the way Irish economy is changing now with tariffs. A lot of people's jobs in the pharmaceutical industry are under threat, and also with like our energy demands, not only because of climate change but because of the war going on in Ukraine. Do you think that Ireland should really start stepping up, not only in the research and development, but also the Irish government should help with Irish-owned businesses that focus on renewable energy storage?
Okay, great question. Does anybody want to take it? I'm looking at Connor, maybe.
It's a should question. So well, without answering your question directly, right? I mean, certainly in the case that we looked at, so we looked at 6 European and 6 non-European countries that were either leaders in storage or were what we call promising markets, right? So places that had big pipelines of batteries coming through. And yeah, I mean, providing all kinds of different financial supports and regulatory environment for domestic businesses, right, that were involved in this sector was a big part of what they did, right? So through tenders and through system services and through spot markets and through capacity auctions and all the rest of it. So, I mean, I guess for each sector, right, so your question is a bit broader, but for each sector it's going to be different, right, what you offer. But these sectors need policy intervention. That was the one common thread from kind of China to California to Ireland, is that public policy is really central to getting these industries going, right, and then keeping them on track, right. And when they are on track, they can kind of fend for themselves a little bit, right. So, for example, in a very brief example, in Denmark in the early 2000s, there was a right-of-centre government supported by the far-right Danish People's Party that came into office. They tried to dismantle Denmark's long-standing, well-developed renewables policy. And because ownership of that sector was distributed among big business, right, big Danish businesses that we know the names of, but also among municipalities that had invested in it, and also among communities that had ownership in those assets, it was able to push back, and it was able to make the government make a complete U-turn within about 5 years, right? So, creating a resilient industry in the renewable space, in the storage space, and so on, is really important, but also having that community buy-in and acceptance is really important. So I don't know how far I've gone away from your question, but that's the answer.
Great, thanks, Connor. Any other questions? So, Kelly?
Thanks. I think mine comes back to the circular economy. So you were mentioning about like recycling and how it's important, and like how we're looking into just disassembling the batteries, but what's being done for or what would you like to see done on the consumer level to make sure that they're educated to know where to put the batteries? So like for your AA, AAA batteries, to put them into the little blue boxes for battery recycling in Aldi, but like for the bigger ones, like the bikes, like you said, they sometimes end up in the wrong places and they're classified as hazardous waste material. What's going to be done, or what is being done to make sure that they end up in the right places and not just in a landfill?
Yeah, so I guess with all kind of e-waste issues and batteries, like we have producer responsibility organisations. So we have 2 big ones in Ireland, We Ireland and ERP. And part of what they try to do is they're funded by the producers. So every time you buy an electrical product, you pay a small surcharge on that funds this, fundamental collection. And then it has to fund the recycling processes as well. And part of that is the education part in schools and things like that. But yeah, we did a bit of research actually. We got it published last, in January, I think it was. And we actually, we're now seeing batteries turning up in products that were normal products that didn't have a battery technology. So now I mean, you now have a battery in your toothbrush. Okay, so there is, and you have, I think light means of transport is a really interesting area because nobody could have foreseen the huge surge in the amount of e-scooters that there are and things like that. And from previous work that we had done on the E2E project, we can see that convenience is a huge aspect of consumer delivery of products back for recycling and things like that. We're doing a little. We've looked at retailers as well that are now have shifted. Let's say bike shops used to have to be part of the producer register scheme, and now they have to be, and that's a massive shift, right? And even if we're sending an e-bike out the door to a consumer or a scooter, how much education are they getting on battery care, on product care, and at the end of life, what do you do with that product? How did you bring it back to the shop? Do you bring it somewhere else? And again, it's convenience it drives it in a lot of senses. So yeah, we're actually still researching that, and it's been really, really interesting. We interviewed 14 people, 14 different kind of actors and stakeholders along the product lifespan. And this was just e-bikes now. We excluded e-scooters and things like that because this was part of the iCycle project. We had some repairers tell us that, oh, every part of an e-bike is repairable. I've quotes from people who said, I've got a guy who recycles batteries. I drop the battery down the road to him. He checks the battery health, battery status, resells it if it needs new cells, sends it back to us. We had other repairers tell us, oh, once the battery's gone, no, that's pretty much it now, it's dead. And that's what you're kind of dealing with on the ground. And, I'm scratching my head going, this is such a waste of stuff, So education is massive. But again, the way that the producer responsibility organisations have been set up is capture, collect. And fundamentally moving that into the circular economy is like our single biggest challenge now. How do we structure those systems? We can't take them apart completely, but how do we tweak them to make them work better? And I don't know if that's the job of an environmental scientist. Again, that's where you need people who are expert in behaviour change, people who are expert in marketing, and even, how do we talk to different groups of people about how their recycling behaviours, habits, what's in the realm of control, We assume lots of things about recycling. So even with hazardous waste recycling, we assume that people have cars to drive hazardous waste to the civic amenity site on a Saturday. That's a massive leap to make. And we really need to start bringing that back. It's interesting that we can look at models like the bottle return scheme, maybe something like that for batteries. Maybe we have to start getting creative about it.
Okay, very good. Look, I think we could stay here all day, but in the interest of time, we're going to have to conclude. So again, well, first of all, I'm conscious that Hugh hasn't had a chance to speak. I'm not going to put him on the spot. I haven't fallen out with him or anything, but it was intentional. He said he was resting his voice after his presentation. But we'll conclude there. On behalf of the directors of AMPEiRE, so myself, Hugh and Kevin, I'd like to thank you very much for turning up and listening intently today and for your questions. Most of all, I'd like to thank the panel again. Though I think it was very, very an excellent discussion we had today, and thanks for sharing your insight and expertise. So thank you very much, everybody.